Hello, folks. This is Sridhar Ramakrishnan. Welcome to our webinar this month. Let's go ahead and get started. Professor Arindam Banerjee will present shortly, and we'll go on till approximately 1 p.m. Pacific time. Professor Banerjee has indicated that he'll stay a little longer to engage in any questions or discussions with those of you that should choose to engage with us. The slides and the recording will actually be available shortly after this talk, both at our YouTube channel, and the slides will actually be uploaded to our account. So you should be able to log in and view both of them. If you've dialed in, please make sure you enter your audio PIN to ask questions, or if you've used your microphone and headset, you should be good to go. You can ask questions either by asking them directly throughout the presentation. Professor Banerjee welcomes questions, or else you can choose to ask questions via chat. Enter your question in there, and I will relay them to Professor Banerjee. Just as an etiquette, please keep your microphones or your telephones, etc., muted. That way, any ambient noise, typing of keyboards, etc., doesn't become too distracting for the rest of us. Let's see. I guess with that, let's go ahead and get started. Professor Banerjee, I'm going to hand it over to you. Hello, Professor Banerjee, can you hear me?
Yes.
Go ahead.
Can I get started?
Yes, please. Oops, I'm sorry. I forgot. I apologize. I was in the midst of getting a bunch of things done. I forgot to introduce you. Let me go ahead and introduce Professor Banerjee. Today we're delighted to have Professor Banerjee to talk with us about online optimization for large-scale machine learning. This is a topic that has got great interest to all of us. And so hopefully it'll be a nice interactive session. Dr. Arindam Banerjee is an associate professor at the Department of Computer Science and Engineering and a resident fellow at the Institute of Environment at the University of Minnesota, Twin Cities. He's received his PhD from the University of Texas in Austin in 2005, where his dissertation was nominated for the Best Dissertation Award. His research interests are in the area of machine learning, data mining, convex analysis, and optimization, and their applications in complex real-world problems, including problems in text and web mining, climate and environmental sciences, aviation safety, finance, social network analysis, and bioinformatics. He's actually won several awards, including the NSF Career Award in 2010, the McKnight Land Grant Professorship at the University of Minnesota, Twin Cities in 2009 through 11, the J.T. Oden Faculty Research Fellowship from the University of Texas Austin in 2006, the IBM PhD Fellowship in 2003 and 4, and 5 Best Paper Awards in top-tier conferences. We are absolutely delighted to have Professor Banerjee talk with us here today. Professor Banerjee, please go ahead.
All right. Thanks, Sridhar. So I'm assuming everybody can see my screen, so I'll get started.
That's correct.
All right. So what I'm going to try to talk about today is online learning and what are online learning or online optimization problems, and give a sort of a brief glimpse at one class of methods which are getting quite popular in this area, especially for large-scale machine learning. So sort of the plan for the talk is, I'm going to sort of establish some of the basic terms like regret and online gradient descent and things like that, and we'll get started with a simple application. It's a sort of a toy application. Let's say we'll call it portfolio selection. The actual portfolio selection work needs quite a bit of additional effort, but I'm hoping this will be easier to follow. One of the main tools that we will be talking about today is something called the alternating direction method of multipliers, and we'll spend a little bit of time understanding what this is and what it can do, and then get into how you can make it online and so on. Then I'll spend some time on an application which is quite popular in some circles in terms of streaming text or tweets and so on. How do you detect new topics of discussion emerging in that kind of a stream using methods in dictionary learning, but essentially using these optimization methods. And then I'll wrap up with a very different application from the domain of climate science on drought detection, but I'll primarily illustrate it from the perspective of solving immensely large linear programs on large-scale machines and how these methods do at that scale. So we'll jump right in. So the portfolio selection is that you have a little bit of money. You're trying to make more money in the stock market. So what you do is you take your whatever $1, $10 and split it up into stocks, right? So and then so you take your $10 and split it up in $2 here, $1 here, and so on and so forth. And then you hope the market sort of moves in the right direction so that you end up getting more money. So in day one, let's say you start this exercise in day one, you invest in the morning before the market opens, and then during the day you're going to just sit down and watch. So what's going to happen is that the market moves in a certain way which you don't have any control over. So what will happen is that some of your investments may have sort of incurred losses, some of them have incurred gains, and so on. So you look at that, and then you say, okay, tomorrow I want to change my portfolio a little bit. And essentially what I mean by a portfolio is that how you are splitting the amount of money you have. Let's say you have $1. What are the fractions that you're investing in the different stocks that are available, right? So this is you can be more creative and come up with other examples where you're allocating resources, maybe your time, to various projects and things like that. So there'll be ups and downs which are beyond your control. In the next day, you're going to, based on what happened in day one, you're going to come up with another sort of portfolio based on how you think the market will move. And again, in the day two, the same thing repeats. We keep doing this. Every day morning, we are creating this portfolio, and every day the market moves in a way that you have no control over. This goes on for a long time, let's say T days. And what you're sort of trying to do is that on the left-hand side, where you're trying to select these orange portfolios, you are trying to select them so that the total amount of wealth gained is maximized in some sense. This is something everybody wants to do. It's just a fundamentally difficult problem, right? So this has the typical flavor of what online learning problems are. This is a bit different from the classical optimization problems, and I'll touch upon that in a little bit. In standard optimization, you are actually giving a function and you are trying to minimize or maximize it. In this case, when you are choosing your solution, when you're choosing your portfolio, you actually don't know what that function is going to be, right? How that day is going to unfold and things like that. We can take another example, let's say sort of spam detection or something like that. You're building a machine learning system which detects spam, but you don't know what new kinds of spam will show up that particular day. So you actually don't know exactly what to design. So there are things beyond your control. So in portfolio selection, we are going to get into a bit more detail, and I'll make it a bit more clear what we mean by optimization in this kind of a scenario. So we'll run with this example for a couple of more slides. So let's consider n stocks over t days. One of the quantities that folks often are interested in, something called the price relative, which is the closing price of stock I on day t divided by the opening price. So if this relative is larger than 1, then that stock gained in that particular day. If it's less than 1, then it lost. If it's equal to 1, it effectively stayed unchanged in that day. And when I say a day, I don't necessarily mean a day necessarily. It can be 1 hour, 1 minute, 1 second, whatever the unit of time you decide. If you're getting into high-speed trading, that day can be replaced by anything you want. What you get to choose is a portfolio vector xt, which is a fraction of wealth in each stock, and it is easy to show that if your price relative is RT, then the multiplicative gain in wealth in a given day is simply going to be the inner product between xt and RT. You invested more in a certain stock, it had a higher price relative, you're going to gain more multiplicatively. And it's multiplicative because of definition of price relative. It's the ratio. So what people try to maximize by choosing these xt's is the total multiplicative gain, or in machine learning terms, we usually like to look at losses. So we would be looking at the minus log of that quantity. This is something we want to minimize. Now this is just an example, and I'm going to illustrate other examples of such problems. But let's go one more step with this. All right. So we want to maximize the wealth gain by choosing the portfolios every day. Now, so let's say these are your T days, and that's the time axis. So if you are here, if you are in day one, if you are over here, and in an ideal case, if you had a time machine, what you would do is that you would go forward 20 years using your time machine. You will look back at the market. All the price relatives will be available to you. You will know the price relative on day 1, day 2, day 3, all the way up to day, after 20 years. And looking at all of these price relatives, you'll say, aha, this is how the market moved. So what I'm going to do is I'll look at all of these price relatives and come up with the best portfolio, fixed portfolio I can in order to maximize my gains. So this is a perfectly good idea. There is only one problem with it, that this cannot be executed because we don't have the time machine, right? So this is the best portfolio, single best portfolio we could come up with. Instead, what we are stuck with is that we have to first pick a portfolio for day 1, or a spam detector for day 1, or whatever your prediction method is, what news story to serve on your web page in day 1, and then what you get is you get a price relative. In day 2, before seeing R2, you have to pick a portfolio, and then you get a price relative. In day 3, you do the same thing. This is the key aspect of online learning, that you are actually picking the solution before seeing what is in front of you, what is ahead of you, right? This is fundamentally different from this time machine idea, which we anyway can't execute. So you go all the way to RT, and the algorithm we are trying to design is to choose these X1, X2s, and so on and so forth sequentially, only based on historical observations. And you can use the historical observations in any way you want. So this is the crux of online learning, and this is how it's different from other types of optimization. But a lot of the themes in standard optimization do show up over here. And then we are going to use this concept called regret. So the first term that I'm showing over here, that summation, we don't have to think too much about it. It's essentially your cumulative loss of your algorithm. The total loss, sum over the losses over individual days incurred by your algorithm, right? And what I'm subtracting from it is the loss incurred by that time machine algorithm, which uses X star, right? So you would expect the second loss to be much smaller. The second loss to be much smaller because this guy actually got to see the entire data set. You didn't. So in terms of loss, this is going to be a larger loss. So what we will do is we will be talking about these in terms of general convex functions. So there will be a sequence of functions ft, which can be any arbitrary convex function depending on your problem. You are getting to pick these xt's, which in this case were our portfolios. Instead of minus log, you could pick something else. You can pick x squared or something like that. But these things change over time. There's a time component, and we expect these things to change over time. This is a forward-going algorithm. XTs are what you choose. X star is what was chosen in hindsight. This is not a practical algorithm, but we are going to try to compete with it. I'll briefly talk about what we want this regret to be small. We want to be competitive with the time machine algorithm in the general case for arbitrary convex functions. Somewhat surprisingly, this is actually doable, and this is doable. The fact that this is doable is known in one form or the other since the 1950s. So this is not even a recent discovery. The literature has come together in the last 10-15 years, where many of the disjoint threads have been pulled together, and I'll give you a brief glimpse at the literature in a bit. So now we are going to officially define what we mean by sort of online convex optimization. So convex functions are functions which which satisfy this property that they have this nice structure with one global minimum on a feasible set, and most of the effort in machine learning ends up becoming optimizing some convex function under some constraints, so support vector machines and other things. The difference in online convex optimization is, if you look at the standard definition of convex optimization, the function is given to you and you are picking the best solution to it. This is different from what we saw in the portfolio world, where you pick a portfolio and then the market unfolds in front of you. So you don't actually know the function when you choose your solution. So conceptually what goes on over here is that you pick a solution x1 to some problem, right? And then there is this function that is revealed to you, convex function f1, through some process. I mean, this may be, social media being generated in a certain way, spam detection, stock market, climate change, and whatnot. We are allowing for analysis that this function can be chosen by an adversary, somebody who is trying to sort of maximize their benefit and minimizing yours. So we have to choose x1 before f1, similarly x2 before f2, and so on and so forth. And I'm saying in the general case, I'm allowing arbitrary functions ft to be used because I don't know those functions ahead of time, and the cumulative loss is simply the sum of these losses on individual data points. If your function is not changing, this is simply the cumulative loss on f. So,
Arindam, I have a question.
Sure.
Are particular kinds of problems more amenable to this kind of optimization? I mean, to this kind of a solution? I guess portfolio selection was one, but are there particular problems that you've seen where the solutions you identify are particularly applicable?
So this approach applies whenever you are trying to do convex optimization, even if your original problem is not an online problem. But you have 100 billion documents and you're trying to learn a classifier based on them. This is simply saying that instead of trying to look at all 100 billion documents at once, you can look at one document. So your function f stays unchanged in that case. You are trying to, let's say, learn a support vector machine or something like that. But you are looking at one data point and updating your predictor, which in this case is captured by x. So in this case, what this is saying is that instead of looking at all 100 billion points at once, you can look at one data point at a time and update your classifier, go to the next data point and update your classifier, and keep going over your data set cyclically. So to sort of directly answer your question, this applies any place where convex optimization can be applied. So it is not restricted in any form. It can additionally be applied to the case when the functions are changing over time.
Thank you.
So the notion of regret, as we presented, is that there is a best you can find in hindsight, and if these functions are not really changing, the best is the optimum. It's a global optimum that you can come up with, and so that's the cumulative loss you are incurring. And the regret, I said, is that the cumulative loss incurred by the forward-moving algorithm minus the total loss of the best algorithm, best solution chosen in hindsight. So the requirement when we are designing algorithms or online learning algorithms is that this difference, we do expect the second term, the thing which has actually looked at all the functions, to do pretty well, and we are trying to compete with it. We want this difference not to grow as fast as t. So we want this difference to grow as square root of t or log t or something like that. What that leads to is that the per iteration regret, in every iteration, your difference from that optimal portfolio will essentially be 0. So you are in the long run going to do as well as the best portfolio your time machine could have chosen. This is surprising, but interestingly, this is doable, and these ideas have been around for a long time. So let's look at the simplest algorithm for doing online convex optimization. Remember, we are allowing your functions to change. If your functions don't directly change, but then you're looking at parts of your data set, that can be applied over here as well. That's usually called the stochastic optimization setting. They are very, very closely connected. So the way you find your next portfolio or your next parameter of the classifier is you come up with a linearized version of your function. You take the gradient of your function at that particular point, and you have an inner product with your unknown thing, and you want your unknown thing to stay close to the previous day's portfolio. That's all you're trying to do. So this particular function is known as the proximal function. It can be the squared Euclidean distance. It can be a KL divergence, in general a Bregman divergence. All you need from the function is a sort of a measure of the gradient of the function at a certain point, which we are calling xt, and this is what we call an oracle for the subgradient. You should be able to compute the subgradient of the function in the previous step. When you're trying to figure out xt plus 1, you're looking at the gradient at time t. So if you use Euclidean distance as this proximal function, you get vanilla gradient descent. So this is your new iterate will be your old iterate minus a learning rate times the gradient of the function. If this function did not change over time, this will be exactly your textbook example of gradient descent.
No. Are you interested in playing every day?
Okay.
Really?
But yeah, today I'm listening to a seminar, so today is not.
Okay. From now on, we'll count you.
Okay. I apologize. Arindam, you there?
Yes.
Yeah, folks, just a quick interruption for folks. Please do keep your microphones or headsets or telephones muted because the background noise that may be coming from your offices, etc., is distracting. I have muted a couple of people who are attending, so because I think that's where the noise is coming from. So if you guys please mute your own microphones and telephones, we can have an uninterrupted session. And if you do need to ask questions and you find yourself muted, please ask the questions via chat. Thank you. Sorry about that, Arindam. Thank you.
Sure. Okay. So, your well-known gradient descent is actually a special case of this. When the function doesn't change, you get back your gradient descent algorithm. The only additional twist over here may be you may have a feasible set you want to stay into. Then all you need to do is something called projected gradient descent, where you take the gradient step, and this complicated looking pi of x simply says that then you project back to your feasible set, whatever that is. We will come back to this in a minute, but remember that things you are very familiar with, like the gradient descent and even the Newton method, can be derived from this scenario. All right, and then you can show that this simple algorithm, the projected gradient descent algorithm, just has a sublinear regret. There are some simple proofs to show these kinds of things. So this is a good algorithm. If you're just going to use gradient descent, that works. Remember to use the gradient of that changing function at every step. Now, I'll give you a quick glimpse of the history. So these ideas have been around since the 1950s by James Hannan and David Blackwell. Some really seminal work they did back in the 50s. And also these ideas showed up in the context of perceptrons and neural networks. The earlier work, in fact, those are actually good examples. A perceptron is a good example of an online learning or stochastic descent algorithm. These ideas, people have gone back to these ideas several times in the literature. The major resurgence was in the late 1980s and 90s. Tom Cover studied them in the context of portfolio selection. It has been studied in the context of machine learning, weighted majority algorithms, learning from experts. There's numerous very heavily cited papers. Littlestone and Wormuth is the weighted majority algorithm. Freund and Shapiro used these ideas in order to develop boosting methods. So if you go back to the original boosting paper, the first half of the paper actually talks about online learning. The last 15 years, this literature has come together really well. These threads have been very nicely tied together. There is now a book by Chisabi and Chen Lugosi which covers I think the book came out in 2006, so it covers much of the sort of the historical development. There have been several surveys and tutorial talks by several people in the last few years. So if you get interested in the area of online optimization or stochastic optimization, there's plenty of material out there for you to look up. All right, so I'll sort of wrap up get into the details of the portfolio selection example with a specific application. These are the high-level ideas. So let's say you're trying to do optimization with K algorithms, and I'll make this concrete. I'll say, let's say you have 5 different rules of thumb for selecting a portfolio, right? And we are calling them 1 through 4. And each one of them suggests a portfolio. And this may be a mutual fund says, go like this. Somebody else says, no, go like that. Well, none of them really know what's going to happen in the next day. So you are looking at these 5 different iterates or 5 different portfolios recommended by 5 different people. And you immediately observe is that if the red point is the optimum of the function you're trying to optimize, minimize in this particular case, the convex combination of these 5 iterates, the best convex combination, which is this green point, will probably be better than each one of them individually. It's just you don't know how to combine them, right? Another scenario can be that, well, there are 5 different portfolios being suggested to you by 5 different people, and you again find out is that there is a portfolio in the convex hull of those portfolios which is quite a bit closer. It doesn't overlap with the best possible, but it's much closer to the optimum than any of the individual portfolios, right? Another scenario can be that, well, somebody is suggesting a portfolio and that's the best among the 5. Any combination only weakens it because you go far away from this. Now, so what we are going to try to do is that, since I don't know too much about portfolio selection, but there are other people who seem to know and they come up with different suggestions, what I'll do is I'll listen to all of them and I'll only try to figure out how to combine their suggestions in order to come up with my own portfolio. So I am after the green point rather. I'm sort of going, I'm listening to these sort of black squares, then I'm trying to get, how should I combine them so that I get this green point which takes me pretty close to the red. The only issue over here is that I don't even know the function, so I don't know the red. So this is the online learning problem. Had I known the red, then I would have gone with that particular best combination. So this is what we call a meta-optimization, where you are not doing the hard work, somebody else is doing it. And you can do this with optimization, as in there are 5 people who have come up with 5 different iterative update algorithms, and you will take all 5 iterates and you'll combine them to come up with a better iterate. Okay, so what online learning does in this scenario is something very interesting. Online learning will be able to guarantee that the green point that we come up with over time will be competitive with the best convex combination you could come up with in hindsight. So if you look back on all the data and you come up with the best convex combination, this forward-going algorithm will be competitive with that. Let me illustrate that with a portfolio example. So let's say let's say method H for portfolio comes up with a certain portfolio XTH. So this is the hth algorithm at time t comes up with a portfolio. Here, go ahead and use this. And you listen to k different algorithms. So you have these k different portfolios. What you are trying to do is you are trying. Yes.
There's a question. 2 questions have come in. Should I take them? Should I give them to you now, or do you want to just finish the slide and then?
No, we can take it now.
Okay. I guess the first question is, online optimization assumes no information for the future, but if you predict future data points based on historical data and use the prediction in the optimization algorithm, could we improve the performance of online optimization?
So the theory analysis assumes nothing about what the future functions are going to be. If we have some ideas on what those future functions are going to be, and if there's a good way to sort of use that, we can improve the nature of guarantees we can give. So quite likely the algorithm itself is not going to change, because the algorithms achieve certain rates which are the best possible, but the analysis will change. You will be able to make stronger statements about what your method is capable of doing. So that's a message I'm going to try to come back to later in the talk, is that coding these things up is very easy. Even if your function is not changing, the same code will work. Even if your function is changing only very slightly, that will still do a pretty good job. So you do not have to customize your algorithm to every possible scenario there is. But if you have a good sense of what is coming in future, there would be a way to take advantage of that, particularly in the analysis.
Okay, let's see. The second question has to do with, does this solution apply only when f of t of x is convex?
We can give theoretical guarantees only when f of t of x, if ft is a convex function. Yes, that's correct.
Okay, and folks, those of you who asked the question via chat, either jump in and respond, or else send me your responses and I'll relay them. Thank you.
I'll just add one more comment to that last response, is that it has to be convex, but it need not be differentiable. It can be the indicator of a set, or it can be absolute value of x and things of that sort. So it need not be something as nice looking as x squared. All right. So what we do is that in this example that I'm talking about is that all I'm learning is the weights I'm going to put on each one of those portfolios, non-negative weights which add up to 1 on those portfolios in order to come up with my portfolio. And how do I choose these weights? Well, these weights are chosen according to an online learning algorithm using, let's say, online mirror descent, which is what I was talking about, online gradient descent. So I'm actually going to show you some results on comparing a few of these algorithms that have come up in the literature by Hemgold et al. This is Power's universal portfolios, the online Newton algorithm, and anti-core. So these are algorithms done by somebody else. We are simply going to combine them, and we have two ways of combination. I have primarily talked about the gradient-based method, which simply does a gradient descent type update as the market is changing. You can also do a Newton type update, which is a second-order update, and there are details in our papers and other people's papers on these. And then we use sort of two simple data sets which have been used in the literature. One is a S&P data set, 20 years going from 1990 to 2010, and there are more results on NYSE. So I'll jump into the results to sort of give you a sense of what happens. This is a logarithmic wealth growth. You start with $1, right? You are allowed to trade as many times as you. So there's no restrictions on trading, and this shows your logarithmic growth in wealth over time, at a daily resolution over 20 years. Now, ONS, this is an algorithm proposed by somebody else for doing portfolio selection. We are not worrying about the details. It is actually hidden. It is this sort of purple-colored line which is hidden over here. The guarantee that online optimization has is that we are going to do as well as the best method in my pool. Now, when you create a pool of such algorithms, unfortunately, you will not know upfront which one is going to do better on a certain data set, on a time interval, and so on, right? So what this is saying is that you can't even see the ONS method because the method I'm talking about, which is meta optimization with gradient descent, exactly tracks it. It has this capacity that it can track the best algorithm. Let me give one more example. I throw in another heuristic called anti-core 30, which is a pretty nice heuristic. It works pretty well on many data sets. There's a very nice paper discussing the properties of these algorithms came out in 2004. We are going to follow this green line, and the property I'm saying that or the theoretical guarantee it has is that it can track the best method. So if you see the green line, initially ONS is doing a bit better. So it's among the winners. Now, as time progresses, the AC30 just takes off and ONS stays below. You see the green line actually now keeps tracking the AC30 algorithm. It may not do exactly the same amount as AC30, but what we said in the regret sense is that it'll be pretty competitive, and that's something we can guarantee without knowing upfront which one is going to turn out to be a winner. We may go through another phase where some other algorithm takes over, and this will immediately sort of go and start following that algorithm. So this is actually a very nice property to have in many scenarios where you have a bunch of rules of thumb and you don't know which one is going to pan out, and this is going to do it for you. This is one of the more popular ways of talking about online optimization algorithms, and this is essentially what regret means, that I'm going to be competitive with the best one in your pool, and this is showing that that's indeed happening. All right, so I'm going to sort of get into the second piece of our talk. So we have got a sense of what this regret business is. We are allowing functions to change over time, and we have talked about the existing approach based on sort of a gradient-based updates of first-order methods based on proximal functions and so on. The problem these methods face in practice is this little thing we ignored earlier, where X may have to belong to a certain set, right? If this set is easy, then we said that we are going to project to that set. But if this set is fairly complicated, and I'm going to show you a couple of examples later in the talk, this projection is going to take another algorithm. So you just need another algorithm just to do the projection, and you'll end up getting a double loop slow algorithm. So the need for projecting onto this feasible set can become the main computational burden. So what I'm going to talk about are these alternating direction methods, which actually has a very nice way of handling this issue. So like a brief one-slide overview of the alternating direction method of multipliers. It is capable of solving problems of the form fx plus gz, where fx and gz are convex functions. They can be things like, they need not be smooth. They can be absolute value of x or indicators of sets and so on, such that they satisfy a linear constraint of the form, generally x plus b is equal to c, some linear equality constraint, right? So the way this alternating direction method of multiplier goes is that you construct using standard optimization techniques what is known as a Lagrangian. So this is called the Lagrange multiplier, ax plus bz minus c. This needs to be 0, so you add a Lagrange multiplier. In this case, you use an augmented Lagrangian. So you throw in another term, which is ax plus bz minus c squared. Now, when you are in the feasible set, meaning ax plus bz is equal to c, the contribution of this term is actually 0. So you are back to your standard textbook Lagrangian, which is the first 3 terms. However, when the constraint is violated, this actually has a positive value, and that's going to encourage, in some sense, things to sort of go towards the feasible set. Now, what is the alternating direction method of multipliers? If I give you this first problem, the original problem, staring at it, we will have no clue as to how to go about doing this. Well, there's a constraint, so we can't really do gradient descent. We can do all those complicated Lagrange dual business. We may not be able to get the dual in closed form and so on. So what ADMM says is that you look at this function. Given any problem, you can come up with this function. Then you alternately update x, z, and y. That's your algorithm, right? So just when you are updating x, keep z and y fixed, and then you only have a function on x, you update x. Don't worry about the equations. That's all I'm doing. Then when you are going to update z, you fix x and y, and you update z. When you are updating y, you can show that this ends up in closed form. So this simply becomes the old yt plus this difference. And when you are in the feasible set, this thing becomes 0. So yt plus 1 becomes yt. This is what your code is going to look like, right? Till convergence, repeat these 3 steps. And that's essentially all there is to it. So and I've said that f and z can be arbitrary convex functions. So that is your algorithm, right? So this is a surprisingly simple algorithm for a constraint problem which can handle arbitrary linear constraints. The only issue with this has been around for a while, is that the rate of convergence was unknown in the last couple of years. Some of us have closed that gap, so now we know how it converges. It's mostly good news. What I would sort of recommend is that there's a beautiful ADMM survey written by Stephen Boyd and colleagues, and there are tutorial videos by Stephen Boyd just talking about this method and what it can do. And I would encourage you to sort of take a look at that. And he illustrates through many examples why this method is so powerful and versatile, especially for large-scale learning. So moving on, I'll give you 2 examples. One is, so we want the problem in this form. People these days have started looking at what is known as a sparse regression or Lasso. So you have a squared loss and you have some L1 term on X. If B is the identity matrix, then this is just L1 on X, then you have the Lasso problem. So this, of course, does not appear in this form, but you can do a change of variables. So you can say, oh, I'll call dx is equal to z, and that will be my linear constraint, and I'll put z over here, and then I have it exactly in the form fx plus gz such that some set of linear constraints connecting x and z. So your problem, optimization problem, once you're formulated, may not be in this form, but a little change of variables may bring out that structure, and then you're all set to go. I'll give you another example, and this is a fairly general one. This is arbitrary optimization with linear constraints. You're trying to minimize over x such that ax is equal to a, bx less or equal to b. This includes things like linear programming, extensively studied, where fx is c transpose x, quadratic programming, where fx is a quadratic function. These are all subsumed under this framework. And I'm going to show you that this thing is actually a special case of this problem. How? Well, all you'll have to do is, ADMMs don't like inequality constraints. So you have an inequality constraints over here, bx less or equal to b. So what you do is you say bx is equal to z, and that z has to be less or equal to b. This is the indicator function. Indicator function meaning if z is less or equal to b, this is 0. If z is greater than b, this goes to infinity. This is your gz. And I said I am allowing indicator functions to be a part of ADMMs. This is an example. So essentially any optimization with linear constraints can be solved by ADMM, right? And you need to be a bit more clever for specific problems like linear programming, that you can get much more out of ADMMs if you do this decomposition in a problem-specific way. But this decomposition will always work. All right, so I've shown that ADMMs are fairly general. Now I'll come back to my story where the function actually changes over time, right, ft. This is the surprising bit, and this is one of the key messages of what I'm talking about, is that if you remember what we had agreed on, we had agreed on saying that we'll update x, keeping the other two fixed, we'll update z, we'll update y. You do the exact same thing. Your code doesn't change except for you plug in whatever that function is which is changing into that line of the code, right? So this is very reassuring, and this is the point I was making earlier, is that your code essentially stays the same. If the function is changing, so be it. If the function stays fixed, then I'll converge, right? And that's really one of the main messages in online. So you can solve constraint problems without going through those painful, figure out the dual, do dual ascent, and so on and so forth, which may not be analytically possible. This is a very, very simple way. The same idea continues to work for the dynamic case. All right, so then I'm going to give you a brief glimpse of the theory. Don't worry. This slide is only to show that all the rigorous guarantees and proofs and things like that work out. For general convex functions, we have sublinear regret. For strongly convex functions, we have even stronger regrets like logarithmic regrets and so on and so forth. These are there in papers written by us, by a few others, and so on. And this story is coming together quite nicely. All right, so I'll get into one application, give you a brief glimpse of a fairly popular application. Is that in social media, people sort of worry about, oh, I have these discussions going on. These may be news items. These may be popular topics in Twitter. These may be something else. And in the next time step, what happens is that I get new news items or new tweets and things like that, right? And some of them, like the blue ones, are going to be new, and some of them are going to be continuations of old things. So these are going to be new, and they get absorbed in these stories. But this seems to be a new story, a new topic of discussion that emerging. There's plenty interest in understanding these discussions as they are emerging, and you want to quickly detect that, oh, there's a new topic evolving, and some people want to sort that as a new. Some people may want to serve advertisements based on that, and so on. All right, so just to give you an example, we had done this jointly with some of my colleagues at IBM Research, and they're saying they were following these tweets during the Jeopardy at Watson, and this is sort of the old tweets which is showing, oh, Watson is IBM Watson's machine is going to be playing this. The next day, the tweets are saying, why did Watson think Toronto is a U.S. city? And so on, and that some other people talking about live on TED.com tomorrow, IBM folks are going to talk about this and so on, right? So other types of discussions are emerging. So if you look at the new tweets, in the first day, they were primarily saying, oh, this is going to happen, and then it has happened, and we are talking about something else. So the next day, you will see there's one topic where people are talking about this Chicago-Toronto mix-up. There are other people talking about things at live on TED.com. And then there are other tweets, right, which really is not a topic in itself. Somebody is just tweeting something which doesn't fit a flow, that isolated one. So you want to detect these kinds of topics going forward. And this is essentially an online learning problem because social media is getting generated as we speak. So you don't want to sort of fix your whatever topic descriptions for the next 5 days. Then you're going to fall behind, right? So I'm going to give you, in the interest of time, a very quick glimpse of this work. There are a couple of ways of doing this. A popular approach is using dictionary learning. So what you do in dictionary learning is that you essentially learn topics that are active. These are what we call topic atoms. These are weight vectors of our English words, which things are getting discussed and so on. and any new document or tweet gets represented as a sparse combination of the atoms. A few of these topics, combination of sports and politics or something like that, discussion about some other things. So there are 3 stages. In the first stage, we detect novel documents. This is using sparse regression. In the second stage, we group the novel documents to get emerging clusters. And the third stage, we update the dictionary as to what topics are currently active. And if you are to do this in batch, which means you store all the tweets for the past month and try to do this, things are going to get really, really slow. So this is one good domain where online learning and online optimization can be done, where you update the dictionary, which is the current topics being discussed in the social media. All right. So I'll give you a very quick glimpse of this. So Sridhar, how much time do I have approximately? Okay, so the idea in detecting new documents is that a new document comes in and we try to represent the new document as a combination of the existing topics, which we call the dictionary, right? This may not be possible. There may be minor errors, and we want the errors to be small as well. So we want E to be sparse, and we want X to be sparse because we are combining only a few of those existing topics in order to do that. So you can come up with a sort of an optimization formulation. This is something we did, and I'm not going to get into the details of exactly how we solve the problem, but it suffices to say that there are sort of 2 ways of going about it. One is you look at the squared loss plus a sparse value on X. That is widely used. That's called Lasso. In many applications, we have found that the noise is spiky, so the squared loss is not a good representative. So we have explored some an L1 loss of the reconstruction plus an L1 regularizer. This is a bit more robust to that type of noise, and you do this optimization. Then in order to do this optimization, you'll see that this is an L1 of the difference plus L1 of X. This is not really, you can't compute gradients and things like that. In fact, if you carefully look at it, this is actually a linear program. But this is a little tricky to solve in high dimensions. If you're operating at 100,000 dimensional space with millions of tweets, just solving a problem like this can become a little tricky. So the way we go about doing this is, if we can solve this problem, if we say this particular error plus the objective is larger than a threshold, what that means is simply that I got large error using many of the topics, but I still couldn't represent it. Then I announce that as a new document, as a novel document. Otherwise, we say that, oh, the document is not novel, it is continuation of an existing topic. So, so this is how the documents are coming in. This is your representation. So this is the document by word matrix. Your representation is coefficients over the dictionaries. And what you're going to do is the new set of documents come in. You're figuring out the coefficients, and you're still using the old dictionary. So this proceeds. The documents which have been deemed new, you pull them out. You find the cluster structure among them. There may be a couple of clusters. There may be a few tweets which are just isolated, and you don't worry about them. Then the question comes of updating the dictionary. So now AT needs to be updated to AT plus 1. If you do it very naively, you have to keep on holding on to all the tweets you have seen so far in order to solve this optimization problem. That's infeasible, right? So in probably a month, you have billions of tweets or documents you have to handle. And this fundamentally becomes infeasible, and it's probably not even interesting. So what we do instead is that we do online dictionary learning, where we only update the dictionary based on the current documents and their coefficients. So we solve a problem like this. This problem itself is difficult to solve. So again, you pull off that change of variable trick where you call this difference gamma, and you minimize the L1 of gamma, like over here with this difference being called gamma. So this is a similar change of variable trick that I had shown earlier while we were going through the examples. And this turns out to be quite a bit fast using online alternate integration methods. So I'm going to sort of skip the details over here, and I'll jump to the results. So the first thing you have to check is that since you're doing this online update and not remembering the old tweets, will you do as good as had you looked at everything? It turns out that this incremental update of the topics actually does almost the same as had you looked at all the documents, those millions of tweets historically and come up with the best possible model. So this is great news. Quality-wise, you don't lose much. In terms of speed, as you accumulate more and more documents, the batch method is going to start becoming slower, whereas the online method pretty much stays unchanged, right? It stays fixed because it's processing more or less the same amount of tweets every hour or every day, depending on the choice you have made. This is an actual run on Twitter, which shows even better performance compared to the batch algorithm. So there are many details in our paper. We actually show the new topics that are getting detected and so on. All right, so I'll sort of wrap up with one other application which has a very different flavor. This is sort of the integer programming type problem. So you have you have a graph, and every node in the graph can take one of k values, right? And you have node functions and you have edge functions. And what you're trying to do is that given these node functions and edge functions, you are trying to find out the most likely configuration, assignment of values. x1 should be 2, x7 should be 3, x6 should be 1, and so on and so forth. So this is the canonical sort of integer programming problem. A whole bunch of things can be posed as this, including your standard NP-hard problems like vertex cover, max cut, and so on. So you can do this for doing community detection and all kinds of social network analysis problems and so on. Over the last several years, 10 years or so, this is of course an NP-hard problem. So what people do is they come up with a graph structured linear programming relaxation, a real relaxation. They come up with a LP which approximates this problem, and in practice it gives pretty nice solutions. And in recent work, some of us have started looking at using ADMMs to solve this linear programming. I'm only going to give you a sense of how scalable this ADMM-based method is for solving linear programs, which has been studied, I don't know, since the 1940s and 50s. So if you have a sense of how big a linear program the existing solvers can go for, probably 1,000 variables, maybe 10,000 variables, maybe pushing to 50,000 or 100,000 variables, but it will take probably 6-7 hours. This is the application we looked at. We actually used this for a drought detection application. I'm not going to get into the details, but if you do this kind of application, you end up finding all the droughts in the last 100 years. And I have a little video in my presentation which actually shows how this thing. These are actually all the droughts, or mega droughts as we call it, in the last 100 years, detected by using this algorithm. But this is solving a linear program. This is how the output looks like. But I'll wrap up with how scalable this linear program is. Right. So we are talking about a linear program derived from a graph with 10 million nodes and 20 million edges. This is something we cooked up. We ran multiple things using the ADMM algorithm. Right. So what I'm showing on the y-axis is the time it takes. On the x-axis, I'm showing the number of processes. Right. So this is solving a linear program with 10 million variables with about 1,000 processes. It takes about 20 seconds for 10 million variables. Right. So this is just to give you a sense of when we say scalable, we actually mean these are scalable. It now matters how much computation power do you have, because these are trivially parallelizable. So they'll solve the linear programming. There are not many other methods out there for solving these kinds of problems which can scale this much. So we are saying 10 million variables, 10 seconds, and the scaling is linear. So if you look at the speed up as you increase the number of processes, so they're an extremely well-behaved method. You see the optimization scales, this red curve scales almost linearly. The IO phase needed some work, but we are doing quite well in the IO phase, and this is going up to 1,024 processes. All right, so I'll sort of quickly wrap up, I gave you a sense of, and just to quickly remind you, this was a batch optimization problem. I'm just solving a linear program. Nothing is really changing over here. So this is going back to the earlier comment, is that if your problem is batch, sure, this will work. It doesn't need things to change. If things are changing, it can still track things. If things are not changing, it will directly convert to the optimum solution. So this is an example of a linear program. So just to wrap up, so I gave you a flavor of what online learning is and online convex optimization is. And I said that if there are no constraints or simple constraints, you can just keep using online gradient descent. If there are more complicated constraints like linear constraints, let's say you have linear programs or quadratic programs and so on and so forth, you want to start looking at these methods. I briefly touched upon 3 applications: portfolio selection, novel topic detection, and route detection, particularly the linear program. And linear programs are considered to be difficult to solve and scale up. And I sort of gave you a very quick illustration that that's not necessarily the case. It depends on how much computational resources are you willing to sort of throw in here, because these methods are easily parallelizable and they can handle streaming data. A few quick papers. The first paper is not by our group, but this gives you a fantastic introduction to alternative direction methods, Stephen Boyd and colleagues. The other papers are by us. We have been publishing this over the last 2-3 years. You should be able to find most of these online. That's all I have. Thank you.
Thank you, Arindam. I guess, folks, any questions on a very, very interesting topic? I guess while people are thinking of their questions, I guess I have one. What would you say, Professor Banerjee, would be sort of remaining items that you're continuing to explore, potentially areas where such a technique does not work? I mean, what constitutes the areas for future research for you?
So one area which is always of interest is to, let's say I talked about this new topic detection in social media or news content serving and so on and so forth. There are other models which are used over there, and in many cases, scaling them up as well as making them more accurate is a challenge. So this is more in the realm of coming up with a formulation on an online problem, which may be ad serving, which may be content distribution, which may be something else, and to see if you can come up. So people have started looking at ranking problems, for example, using ADMMs in search engines and so on. So that's one area where we do expect to see quite a bit of work in the next several years. This is more like this is a reinvention of a method which has been around since the 1970s. And some of us are sort of making a big push for this method. Is extremely simple. It just scales to very large problems. Tell us what your problems are. There are other actually more technical questions that need to be resolved that people are working on. Some of them involve so there are specific types of combinatorial problems or problems which can be approximated by higher order linear programs, and some people are exploring that. But I do expect us to see more applications, clever applications of ADMMs in the next several years.
Thank you. One question has come in online, and the question is actually just following up what you just said. Are you aware of any, industry uses of this ADMM technique currently?
I mean, so the first bullet point I have, which is Stephen Boyd's survey on the topic, it cites very extensively a large body of literature in many different disciplines which use this method. The use of this method on sort of more so the social media type things and other types of things have been limited, but we are hoping that people will start seeing this. I mean, gradient descent is more widely known, right? Even when you're doing optimization, you do gradient descent. But people hesitate to go for constraint formulations because once constraints come in, optimization becomes a little tricky. You have to go to the dual, do complicated things. So the main message over here is that that's not the case. If you have linear constraints, that's easy to handle. The second message is that these things are easily parallelizable. And the third thing is that they can handle dynamic problems. So I don't know for a fact, but I know folks at Google New York, Corina Cortison team has been looking at these things. They are working with Stephen Boyd on ranking problems in large scale. I probably don't know of others, but there are many applications that the Boyd's survey talks about, which is worth looking at. So things like support vector machines, it's an easy application. It's a quadratic program. You should be able to get extremely scalable SVMs using this method, for example.
Thank you.
Any
further questions?
I had a couple of questions. So one was, the ADM method relies on FT-1 being somewhat similar to FT. So some domain knowledge is important. Would you agree with that?
So the analysis does not. So FT, so you don't need FT and FT-1 to be similar in any sort of way, other than you want their gradients to be bounded, and that pretty much covers most things we work with. So in no way for this analysis and for these algorithms to work, you want FT and FT+1 to have any similarity, other than just the fact that their gradients should not go to infinity.
Okay. And the other question I had was, I know in the portfolio selection problem, you were focusing on minimizing regret. Does the regret have a dollar value on each day, or I mean, does the value for the regret map into a dollar value?
You can do the mapping. So what the regret was on the log gain in wealth or log loss in wealth multiplicative one. So it is possible to get. I think in many cases in the plots I showed, it is possible to actually get. And I think Tom Cover's paper talks about it. You have to exponentiate it in order to get the regret in the dollar value. But I have to also add that the example I used is largely illustrative. There are if you get into that domain, I mean, I didn't even talk about risk, right? So without considering risk or trading every stock every day, these are not necessarily good ideas that one wants to go with. And there has been ongoing work in the machine learning community to try to pull these things in. I mean, of course, in finance, there's a huge body of work on this, but people are starting to look at this more carefully in the machine learning community as well, considering risk in particular. But those have to be included for the portfolio selection application.
Okay, thank you.
Folks, any other questions?
Yeah, I have a question. This is on the Twitter example. The dictionary that you define there, so you're kind of defining a particular topic based on the tweets coming in and the dictionary that you have. But when the topic changes, your dictionary, what do you do about the dictionary? Does it dynamically add the new topic or the new items into the list? How does that work?
So you have a few options. The specific run we did, so the specific run we did was that actually let me go to this other picture. Yeah. So for our specific run, what we were doing is that at every step after, and by step I mean, it's 6 hours or a day or something, whatever the unit of time is when you want to update it. So AT was your old dictionary. You processed a bunch of new tweets, let's say PT, and then your new dictionary will be AT+1, right? So your dictionary does change. There's a discussion that we had with the folks who are using is that we should also allow the size of the dictionary, as in the number of active topics, to change, and which makes a lot of sense to me. For the specific runs we did not consider that, so we kept the number of active topics fixed. but one can in principle also change the number of active topics as part of the optimization. But this is definitely changing the active topic, the set of active topics, as it's processing new bunches of social media coming in, because you want to track the active topics, and that's why we spend that time figuring out, is it one isolated tweet, or are many people starting to talk about this? That means we need to allocate this as a topic. The point is that you can pull this off without having to maintain the historical everything that you have seen so far. You can do this incrementally, and then you can guarantee theoretically that what you are figuring out is going to be pretty close to what you would have done had you kept everything, and that's reassuring, right? So you are not throwing them away and forgetting about it.
Okay, thanks.
Okay, folks, any other questions? Okay, I guess if there are none at this point, thank you all for attending. Professor Banerjee, we have a custom here because we are not actually all meeting in a physical room. We have a custom of giving the speaker a warm virtual clap. So at this point, please unmute all your microphones and extend Professor Banerjee a warm thanks and round of applause.
Thank you.
Yeah, thank you so much, Professor Banerjee, for a great talk. The slides, I know you said you were going to compress them. I already have them on my machine. If it's just a matter of encoding the video, etc., I can do that. But if you're going to send me new slides, please do so, and I'll upload them to the site later this evening.
So if you're okay with the slides, I think I have those slides, so you can use them.
Okay, great. Okay, I think I'm okay with that. I'll be recording. This recording will show up on YouTube shortly. It takes a little while for me to process it and upload it. But please do fill out the seminar survey that you see when you exit. That's important for us both to improve the tools we use, etc., and that'll be very valuable. If you do need to engage with Professor Banerjee, his coordinates are on the slides. You feel free to contact him directly, or else contact me, and I can, relay questions or put you guys in touch, etc., etc. Thank you so much, all of you. See you on September 20th when we'll have a talk on. I guess the topic is open source distributed SDN OS by Dr. Umesh Krishnaswamy working at OnLab. Thank you so much. See you on September 20th. Bye-bye.
Right, bye.